Okay, so today's topic is topic one, which is focused around the mole, whether it's the measurement of particles in a gas, liquid, solid, or the reaction between a substance to form another substance. And so we have to establish a couple of things that are kind of standard understanding. One mole, according to Avogadro's number, is 6.02 times 10 to the 23 of anything, units, really. Because the word mole doesn't imply any unit. So every time you see the word mole with something, you'll notice that there is a description of mole after that. So you might say 1 mole of carbon atoms or 1 mole of water molecules. That's important because mole is just a descriptive number, not an actual um, direct connection to the substance you're talking about. It's just like you would say a dozen donuts or a dozen cars. The word dozen doesn't mean anything until you attach something to the side of it. And so that unit could be a lot of different things. It could be a molecule. It could be atoms. It could be ions. It could be formula units. And so it could be other things too. But those are the main units for moles that we'll see. And so it's important that you kind of understand that. And the word mole is just a substitute for 6.02 times 10 to the 23 for something. Now, before we get into the stoichiometry aspect, let's just kind of stick to the basic conversions of moles to grams and particles. And what you kind of want to understand conceptually here is that every number has um, aspects of it. And so you have, like, let's say 3.5 moles of H2O molecules. And this number has really three aspects. It has the value. It has, maybe if there's present, a descriptor, and then it has the actual unit. And it's important that you recognize these things in every number, every value you're given in chemistry, because that affects how you convert. Okay, and the IB, the first couple of questions on multiple choice are often these kind of mole to mole conversions to see if you understand what's going on. And so every time you manipulate one of these things, the value changes. So if you manipulate the descriptor or you manipulate the unit, your value changes by the conversion factor. And those conversion factors are kind of fundamental to all of these calculations. And so what we're going to focus on, and so let's say, for example, I wanted to know how many total molecules we had in a substance. Like if I wanted just H2O molecules and I wanted to get rid of the word moles, I would need to multiply by what that descriptor means, which is 6.02 times 10 to the 23rd. So then I would take 3.5 times 6.02 times 10 to the 23rd, and that would tell me how many total molecules I had. In this case, it would be 2.107 times 10 to the 24th molecules. Okay, and so to get rid of moles, you have to multiply by 6.02 times 10 to the 23rd. To convert 2 moles, you have to divide by that. Okay, now, so really pay attention to what the question's asking, because sometimes the IB will ask, given 3.5 moles of H2O molecules, how many moles of hydrogen atoms are present? Okay, so within 3.5 moles of water, they're asking how many hydrogen atoms are present. Well, the key thing here is you're still in the unit of moles. So you should never be using 6.02 times 10 to the 23rd because the descriptor stayed there. So that's not what's being changed. What's being changed here? What's being changed here? The unit. So you have to do a conversion for that unit. And so what's your conversion of molecules to hydrogen atoms? How many hydrogen atoms are in one molecule here? 2. So therefore, if I have 3.5 moles of water molecules, then how many hydrogen atoms do I have? Huh? 7. Yeah, because you have to multiply by 2 to get to hydrogen atoms, so therefore it's 7.0 moles of hydrogen atoms. So you really want to focus on those labels and how you manipulate those things. Because there's 2 atoms in every 1 molecule, so you have more hydrogen atoms than you actually have of molecules. And that's something that sometimes students struggle to grasp with, because they always think like the whole is made up of the parts, so you can't have more parts than you do whole, but that's not true. It's just like you have more shoes than you have pairs of shoes, right? And so sometimes students think, well, if I have 2 hydrogen atoms, I must divide by 2. That's not like, it's not the conservation of particles there, because the parts can always be more than the sum of those parts into new molecules. And so with this, you're really converting and you're kind of focusing on these units, okay? And I really want you to kind of focus on that when you're looking and reading numbers very carefully. If they have the word moles or they don't have the word moles, know that you should kind of be expecting different numbers, right? If you're dealing with moles, your number is going to be reasonably small, relatively small, maybe in the decimals or maybe in the integers, small integers. But if you're dealing with total atoms or like not the word moles, then you should have a number that's in the 10 to the 22nd, 10 to the 23rd, 10 to the 24th. And so if you're talking about actual number of atoms you have, it's going to be a huge number, like 2.107 times 10 to the 24th. But if you're dealing in moles, it's going to be a number like 7 or 0.4 or things like that. And so it's kind of one of those kind of check methods where you go, okay, they want the number of atoms in this sample, then this should be a huge number. If they want moles of atoms, then it should be a pretty small number. And so thinking about that helps you kind of mentally check whether your number makes sense or not. And that's what, in every chemistry calculation, that's what's really important. And so all these conversions are based on these definitions that we assume are true. Like we said, 1 mole is 6.02 times 10 to the 23rd particles, whatever that might be. We also assume that 1 mole is equal to the molar mass in grams of a substance. That is also a true statement. And we also assume that 1 mole is equal to 22.7 decimeters cubed at standard temperature and pressure for a gas. And when you're doing conversions, these are the only 3 conversions you can have. There's no other conversions that you can use to really kind of manipulate these amounts. So we're limiting ourselves and kind of only giving us choices here. And you see in all these conversions, the universal unit that's in all these conversions is what? 1 mole. So no matter what your conversion is, your goal is always to get to mole and then go away from that, okay? And so I want you to kind of think about that. And that's kind of where the mole map and things like that derive from. I'm not personally a huge fan of the mole map because, again, like I've said before, memorizing things like that, if you misremember something, you have no idea whether you're misremembering or not, because you don't understand why you're dividing by the molar mass here or why you're multiplying by the molar mass here. And so you want to make sure you kind of understand that. And so with these conversions, I kind of tend to think of it in this manner where you want to make the numbers make sense. You can do proportion. You can do a proportion, which a lot of students do because it's very similar to math in that area. So like if they have, let's say our problem is 1.5 moles of N2 gas, and we want to know how many grams of N2 gas that is. Well, in a proportion, the units have to be the same across because they are equivalent to each other. So you know that your unit up here will have to be moles of N2, and the unit down here will have to be grams of N2 because they have to be the same across. And this conversion is always one of these 3 conversions here. So in this case, we will use the 1 mole equals molar mass in grams. So you will do 28.02 is equal to 1 mole of N2, and you cross multiply. Oops. And that equals 42.03 grams. Does that number make sense when you have 1.5 moles? Because you know 1 mole is 28. So if you have 1.5, your answer better be larger than 28. Y'all see what I'm saying there? So it's kind of about that logic and that reasoning. If you are a factor label method, it is a slightly different process, but it's the same answer you're going to get. Okay. The factor label method uses each conversion as a fraction and that you multiply by to cancel out units, kind of like you can also do in math. And so this problem, the exact same problem, would look like this. In factor label, you're multiplying by conversion so the units cancel out. So you multiply here by 1 mole of N2 is equal to 28.02 grams of N2, and you still get 42.03 grams of N2. Either way, for these simple conversions, do it whichever way you feel comfortable. There is no right or wrong way. Do which way makes sense to you. If you like setting it equal to each other, do that. If you like factor label, do it that way. There's pros and cons to each based on the way you think. Factor label, what's nice about it is that you can do a multi-step problem just kind of back to back to back without having to touch your calculator until the very end, because you know that you set it up right because all the units cancel out except for the unit that you want. So factor label, you can do a 3 or 4 step problem all in one line and then just get the answer. Okay. But that's trusting that you know all the pieces that kind of fit in there. Proportion method seems to be a little bit more organized for students. They like to do one little step at a time, and so it goes kind of piece by piece, and they type in the calculator each time and kind of can check themselves. Because in proportion, you're only doing one step at a time, so you can see if your number makes sense each step of the way. In factor label, you're kind of trusting yourself that everything's set up right, and you just kind of put it in your calculator and you get an answer. So there's pros and cons to each. I will be honest with you, I grew up learning factor label method, but I'm not saying it's a better method for everyone. So either of these conversions are really kind of the way that you want to convert that. And so we're always using one of these 3 conversions here as our proportion or our conversion factor in this. Okay. Questions about that? Okay. So once you do that, though, you have to introduce the concept of stoichiometry. And stoichiometry is using the relationships between substances in a balanced reaction to determine quantities. That's kind of a strong definition, but that's the idea. And so using relationships between substances in a balanced reaction to determine quantities needed or quantities produced. Okay. And I'm going to show you a bunch of different ways to solve this type of problem, including proportion and factor label, but then also 2 other ways that you may want to do it. And please raise your hand if you want any clarification about how we do these, but I'm going to do a sample of each of these problems. But stoichiometry. When you have a reaction like, I'm going to keep it simple right now. The combustion of hydrogen to form water. Okay. The relationships you're talking about are these coefficients, because what those coefficients mean is that 2 molecules of H2 react with 1 molecule of O2 to form 2 molecules of H2O. So this is 2 molecules react with 1 molecule to form 2 molecules. But you can keep magnifying that. You could say 20 molecules and 10 molecules make 20 molecules. And we do that all the way until we get to 2 moles of H2 react with 1 mole of O2 to make 2 moles of H2O. And this is what we care about here. And this is our mole to mole ratio. So these coefficients now represent moles, which are a unit that we can used to interconvert between substances, because we can't do grams, we can't do decimeters cubed. Well, we could do decimeters cubed, we'll talk about it later, but we can't do grams because masses aren't equivalent. So we have to convert substances in a unit that is universal. Yes, Tamor? Oh, MLC is just abbreviation for molecule. Yeah, sorry. So molecules, molecule, and then if we magnify it enough, we can go all the way to 2 moles. So 2 times 6.02 times 10 to the 23rd, and 6.02 times 10 to the 23rd makes 2 times 6.02 times 10 to the 23rd molecules of H2O. So we're just showing that that ratio is always fixed. Okay, and so because it's mole to mole, all of your conversions will go toward mole and go away from mole. And so whenever you're trying to convert between substances, you're going to have that idea in mind that whatever you're starting with, you need to get to mole somehow and then go back. Okay. And so you not only have, let's say, how do I do it? You not only have 6.02 times 10 to the 23rd particles in 1 mole, and you not only have grams per 1 mole of substance, you also have 22.7 decimeters cubed of 1 mole of gas. But there's another conversion in here as well that we introduce, which is molarity. Okay, and molarity is moles per 1 decimeter cubed of solution. So that may be another conversion that you're going to have to use in this. This is molarity. Okay, so this is another way to measure the amount of something in our reaction. So most aqueous solutions are measured in a concentration like this. So that gets introduced into this as well. Okay, but all of them still have the word mole in them, so they're all useful in these calculations. Okay, so let's do a kind of basic calculation, kind of show you how you would apply this concept to in kind of 4 different ways. So I'll rewrite H2 plus O2 like this. Okay. Let's do kind of one where I say if 10 grams of H2 react with excess O2, how many grams of H2O are produced? Okay. So if 10 grams of H2 react with excess O2, how many grams of H2O are produced? Okay. Now, we could do the proportion method, and we're starting with 10 grams of H2. What do we have to convert our H2 to? Moles. Everything's always to moles. If it's in moles, then you're already 1 step ahead of the calculation. But here, we have to convert this to moles. And so I'm going to say, well, how many moles of H2 do I have? Well, I know that 2.02 grams of H2 is 1 mole of H2. And notice very carefully, I'm writing all my units out, because when you start doing stoichiometry, you lose track of which substance you're talking about if you don't write all your units out. So I'm very deliberate about writing these units out so that you can kind of keep track of things. So once I do this, I get 4.95 moles of H2. Now, once you get moles of H2, you can interconvert with another substance, because we have a ratio between H2 and H2O, which is the mole to mole ratio. So you would say 2 moles of H2 is equal to 2 moles of H2O. So if this is 4.95, then what's the bottom here? 4.95 as well, right? Because it's the same ratio. So we will figure that it is also 4.95 moles of H2O. Then we can take our 4.95 moles of H2O and convert it back to grams, because 1 mole of H2O is equal to 18.02 grams of H2O. And you get approximately 89.21 grams of H2O. Questions about that? Oh, sorry, I'll give you a chance to write that down. What's up, Muffy? No problem. It's okay. I I appreciate you checking, because I make mistakes. That's not true. Um, Never mind. So one way to set up this problem, step by step. So we go to moles, then we need to convert. Once we get to moles, we convert between the two substances, and now we have the new substance, and we can convert back to grams here. If you're doing factor label, you will write this all in one line across. So you will start with 10.0 grams of H2, and you want to convert grams of H2 to moles. So you want grams on the bottom and 1 mole of H2 on the top, 2.02. Now, once you have moles of H2, you can convert that. 2 moles of H2 to 2 moles of H2O. That cancels. And then 1 mole of H2O is 18.02 grams of H2O. And then the moles of H2O cancel, and you're left with grams of H2O. And all this is, bless you, the same thing as you did in proportion. So you should get the same number, 89.21. Yeah, I think so. Yeah. So, but there are other ways to do it as well. And so I'm going to show you 2 more ways to do it. But again, to each their own. I'm not going to push one way on you. I just want to make sure that, like, if you have a problem that just has random units, like, for example, they just had theoretical units on there, you'd be able to solve that problem understanding the conversions. Like, if I just turn this into, like, I don't know, kilometers and, like, miles, or no, like, I don't know, centimeters to miles, if you know all the conversions, whichever way you think would make the most sense to you, do it that way. It's all about trying to reinforce instincts, because when you're in the stress of a test, you kind of fall back on what you think and what you feel is right. And so some of you may end up switching in the middle of a test to try to figure out how to do a problem. And so I want you to make sure you're kind of comfortable here where there's not any stress, so that you know that you'll be able to do it that way on the actual test. Okay, the other ways are a little bit kind of interesting. Let's just put it that way. And so what I say, the third way is what I call the super equation or proportion. Okay. Now, it's not an end all be all, like one thing. You have to do some work outside of it to make it work, but it's the same concept. And what I do is, in these problems, my right side is always my mole to mole ratio. Okay, it's always my mole ratio of what I want to what I'm trying to get to. And on my right side, what do the units end up having to be on this side so that this proportion is true? What units do I have to have on this side? Moles of H2 and moles of H2O. So there are ways, depending on what amount I have, to solve for each value, right? So in this problem, I have 10 grams of H2. So how would I solve for the moles of H2? I would divide it by its molar mass, right? So would you agree that if I said 10.0 grams of H2 divided by 2.02 grams of H2, I would get moles? Yes. Okay, so that gets me moles on the top. Well, How would I get moles of H2O? Well, that would be X grams of H2O, whatever that is, over 18.02 grams of H2O. Huh? Okay, good. It's not for everyone, but so the goal here is you have to convert this to moles somehow, and you have to convert this to moles somehow, right? Some people might just leave this moles and then solve it separately out, but I'm just trying to show you kind of super equation. So if you cross multiply everything here, you'll get 89.21 because it's still true. It's just a manipulation of kind of the proportion method. Some people might not like this, and that's okay. So the super equation means whatever way it takes for you to get moles on this side and moles on this side, do it and plug it in and always set it equal to the mole ratio every time. Okay. The fourth way, and there's a reason why like you didn't really learn this way in 10th grade because you had really never seen an ice chart before, so it didn't really make sense for you to kind of learn how to do this. But so you can do it as stoichiometry as an ice chart. Okay. And so what you do is you set it up like this, and it's I, C, and E. And everything in here has to be in moles because remember, grams don't convert. And so everything has to be in moles in this scenario. Okay. The amount of O2 doesn't really matter, so we can skip that part. And we start with 0 H2O. What we start with in H2 is 10 grams. So if we convert our 10 grams of H2 to moles, we get 4.95 moles of H2. Now, if you remember from ice charts, we set change to be X or a proportion of X. Well, if oxygen is X, how much did H2 change by if oxygen's X? What factor did H2 change by if oxygen's X? 2X, because there's a 2 here instead of a 1. So this would be minus 2X. Okay. How much did H2O increase by? Positive 2X. Okay. How much H2 should we have at the end of this reaction? Yes, Mofe. Oh, because it's reacting. So it's being used up. So Mofe, how much should we have at the end of this reaction? 0, exactly. So if this is 0, yep. So the change here is minus 4.95, which is equal to 2x, which then means this is positive 4.95, which means you've produced 4.95 moles. So because this all has to react, right? And the ratio between this is every time this goes down by 2x, this goes up by 2x. So if this goes down 4.95, this one goes up by 4.95. So then therefore it just adds downward. This is good reinforcement for ice charts as well. Taymor and Mofe. Yeah, sure. Okay, O2 is crossed out because the problem said excess O2. So it doesn't matter in your calculator. You could solve for it if you want, but it doesn't really matter because there's just a bunch of it. Oh, because you start with no product. Yeah, so you're producing that from that. Mofe. Okay, so the benefit of using ice chart is probably something that, or twofold. Okay, one, you have to use ice charts in equilibrium as well. So it's kind of a double dipping in the same concept. And two, there is one kind of specific time where it is beneficial, I think, and that's when you do limiting reactant and excess remaining. Because in this chart, all your information's here. Like in all the other ways, you have to kind of solve for stuff and then like figure things out. But if you do it in this method, it always works. Like it's all there already. So all of these ways to do it save you time in some scenarios and then cost you time in other scenarios. So that's why I don't say one way is the best, because if it's a limiting reactant problem, an ice chart might be the fastest way because then you can just kind of figure out what runs out first. But if you're just doing a simple, like one where you're going grams to grams with excess, then maybe one of these other ways is faster, but then it's slower and limiting reactant. So there's no speed benefit for this. I'm going to tell you this right now. There's no way that is just inherently faster than the others overall. It's the way your mind thinks. Because I do fact label because I'm so used to it. It just comes boom, boom, boom. If you're a proportion person, you may do proportion faster than me. That's not true. You'll do it faster than other students. Okay, but that's what I care about here is just doing it the way that makes sense to you. But so yes, the ice chart benefit is that you can get the limiting reactant and excess reactant really quickly because it's already all in the chart. You don't have to do an additional calculation for it. So 4 completely different ways to do a problem. Okay. Questions about that? Okay. Let me propose a problem to you to see if you're really kind of being able to do it, and I'll pause the recording while I give you some time to do that, and then we'll see which way y'all want to try it and which way you works best for you. So here's the problem. Um, okay. The molar mass of Na, I believe, is 22.99. The relative molar mass of Cl is 35.45, and then you can figure out the rest for that. Okay. Let's see. Okay. What volume of Cl2 gas at STP is needed to react with 70.0 grams of Na? Of Na. You end up doing conversions here, and so I'm just going to do it fact label here to show you one way to do it. So we use the conversions here. Oops, 2 moles of Na to 1 mole of Cl2, and then 1 mole of Cl2 is 22.7 dm cubed of Cl2, and everyone, I believe, gets 34.6 decimeters cubed approximately. Yeah, rounded a little bit. If you set up a proportion, you're just going to set each proportion to each other. And so I'll set up that really quickly. So 70.0 grams of Na is equal to 22.99 grams of Na over 1 mole of Na. And then X moles of Na. And then that answer is like 3.04 moles of Na. And then 2 moles of Na is 1 mole of Cl2. And then that means 1.57 or 1.52 moles of Cl2. And then you just convert, because 1 mole of Cl2 is 22.7 decimeters cubed. So of that. Okay. Now, where this gets a little bit more challenging is when you get into limiting reactant. Okay. And so with limiting reactant, the issue is now you have amounts of both reactants. Okay. And when you have amounts of both reactants, one is bound to run out first. And that will limit product made. Okay. And so You could think of this as one of two ways, okay? You could think of it as, well, if I figure out how much product each of my reactants can make, whichever reactant makes less product, that's my answer. Because you can't make more product than the limiting factor. Or you want to think of it as, well, if I have one reactant and I know how much of the other reactant I need, if I need more than I have, then the other reactant's limiting reactant. But if I need less than what I have, then that's the limiting reactant. And I'm going to put that, kind of show you how to do that now in both ways, okay? And so let's say, just kind of for simplicity's sake, we'll use that same reaction here with the water one, okay? And let's say I'm given 8 grams of H2 and 40 grams of O2, okay? There are two ways that you could do this, okay? You could ask yourself, which produces less product? So in this occasion, you would take each reactant and, assuming the other one was excess, how much product you could make from that. So that's one way to tackle it. So you would say, well, we'll just do fact label one, we'll do proportion the other. So 2.02 grams of H2 is 1 mole of H2, or 2 moles of H2 is equal to 2 moles of H2O. And I get 3.96 moles of H2O. Why can I stop at moles? Why do I not have to go to grams here? It's the same thing. So if I do that for every single problem, I'm going to multiply by the same number each time. So you're still going to get the same comparison. So you can stop at moles here if you want to do that. Now, you could also do 40.0 grams of O2, proportion method, 32 grams of O2, 1 mole O2, X moles of O2. So 40 divided by 16, or 32, sorry, gets you 1.25 moles of O2. And 1 mole of O2 is 2 moles of H2O. So you could produce 2.50 moles of H2O. So with this amount of H2, I can make almost 4 moles of H2O. With this amount of O2, I can make 2.50 moles of H2O. So therefore, O2 is the limiting reactant, and you can only make 2.50 because you'll run out of O2 before you can make 4 moles. That's the concept there. So I'll admit, when I learned it, that's kind of the way we were taught to address it. No. Sorry. To calculate the amount of product, the same product for both reactants, and figure out which one made less. But there are other ways to do it, and I'm going to show you that too. And this is kind of where the ice chart comes into play too, and I'll show you that what I'm talking about here. The second one, oh, question? Okay. The second way you could approach it is, how much of the other reactant do I need? Okay, so you can ask yourself, well, okay, how much of the other reactant do I need? Okay, so I could do 8 grams of H2 and convert to O2. Oh, sorry, 2 moles of H2 and 1 mole of O2. And here I do want to convert to grams because I'm comparing it to grams in my problem. So what I do here is 8 divided by 2.02 times 32 divided by 2. And I need 63.37 grams of O2. to react. Okay. So my problem here is that 63.37 grams of O2 is greater than the 40 grams of O2 I have. So therefore, this is my limiting reactant. You were just kind of looking at it, Melvin. It's okay. So that's another way. So whichever way you want to do it, they both work fine. You know, if you're just trying to find a limiting reactant, maybe the second way is faster. But then you still end up having to figure out how much product you make if they ask you that question. The first way, you find out how much product you make at the end, but it takes a little bit longer. So again, the speed of these types of problems, it doesn't matter. The IB gives you plenty of time to do every problem. Okay, every mark on an IB test gives you, I believe it's a minute and 15 seconds every mark. So that's actually that's a lot of time. So like a 3-mark question gives you almost 4 minutes to work on that question. You know, I would say that my tests are about like 30, 35 marks, and then you have 45 minutes. So you have a little more time than you have on my exam time. Yes, Taymor.
What are the timings
For SL, paper 1, 2, and 3 is 45 minutes because you have 30 questions. Actually, it's a minute and a half. I'm sorry. It's a minute and a half a mark because for standard level, it's 45 minutes for 30 questions. And then their paper 2 is 50 marks in an hour and 15 minutes. Yeah, an hour and 15 minutes. And then their paper 3 is an hour for, I believe, 40 marks. So yeah, an hour. No, it's not too bad. You have plenty of time. Like, I don't think you're going to run out of time on this exam. Like, as long as you're doing everything and you understand and you're kind of moving through things and not wasting time, you'll be fine. Mofe. Uh, I think they have a giant clock up there. I don't know if you're allowed to bring watches. You'd have to double check with Miss Van Dyke. But what's your second question? Oh, that's a good point. I hadn't thought about that. But like, yeah, if you're looking at a multiple choice question and it takes you like more than a minute to think about it, you need to move on, right? Because you'll make up time in other questions that are faster. And so, yeah, that would not be a bad idea. But I feel like she doesn't let you use watches. Um, Definitely not smart watches, obviously, but maybe an analog watch. I don't know. You'd have to ask her. Okay, now there is another way to do it that is um, it's kind of the ice chart, but also kind of just conceptual. And so we'll do it in ice chart form because I think this will kind of help explain it. So with ice chart, okay, I, C, and E. So we figured out already. I'm going to write this down because we already know this. But so um, we have 3.96 moles of H2 and 1.25 moles of O2 and then 0 H2O to start with. Okay. Our C here is minus 2x, minus x, and plus 2x. And one of these has to go to 0. The way I do it is this. I take my initial and I solve for what x would be. Okay, so I solve for what x would be. So what I do is this. Outside of my chart, I do 3.96 over 2. And I do 1.25 over 1. So my x for this would be 1.25. And my x for this would be approximately 1.98. Okay. Well, which x should I use? 1.98 or 1.25? 1.25. Why, Melvin? Okay, because everything gets to react. And what if I did put 1.98 in there? What would be the problem? You get a negative number. So if you want a quick and dirty way to figure out the limiting reactant, solve for the moles of each reactant, divide by the coefficient. Whichever one's smaller, That's your answer. If you want a quick and dirty way, if you really understand what you're doing, that's a kind of quick way to do it. But since we know this is 1.25, this ends up being 0. This is minus 2 times 1.25, and this is plus 2 times 1.25. So this is 2.50 moles, and this is 1.46 moles excess. So O2 is our limiting reactant. We figure out how much product here, and we actually figure out how much is left over as well. So some benefits the ice chart. So you always choose the smaller x once you divide by the coefficient. Because if you think about it, once you get to that step where you divide by the coefficient, the steps are all the same after that. So if you get to that point, nothing changes after that. So ice chart is another way to do it. Questions about that? Let's see. Okay, let's move on to, well, not really move on, but let's incorporate something else, which is gas law stoichiometry. Okay, so gas law stoichiometry involves obviously the volumes of gases, which we did talk about before, which is at STP 22.7 decimeters cubed is equal to 1 mole of gas. Okay. Now, if I have something like this, and let's pretend they're all gases. Okay. And let's say I had 5 decimeters cubed of N2 gas, and I wanted to figure out how many decimeters cubed of NH3 gas we could make. Okay. Everything looks similar so far. Okay. So what would you first do with this number? Convert it to what? To moles. Okay, I'm going to do it fact label because I think it'll show my explanation a little bit better. So 22.7 decimeters cubed is equal to 1 mole of N2. Now that we're moles of N2, what do we do? Exactly, moles of NH3 from moles of N2, so that's 1 to 2. And then 1 mole of NH3 is 22.7 decimeters cubed of NH3, which ended up getting you 10 decimeters cubed of NH3. Okay. Let's write this down, then I'm about to ask you a question. Because some of you may have noticed something in this problem. Okay. Yes, Tamor. Okay. Does anyone have any observations about this problem that we just solved? Anyone have anything that we could do to simplify it? Yes, Melissa. Okay. Why is that, Melissa? Using the mole ratio, why is that? Okay. So in this problem, what cancels out, Melissa? The 22.7. Because every gas at STP, 1 mole of it occupies 22.7 decimeters cubed. So the mole to mole ratio is the same as a volume to volume ratio. So you can save yourself steps by just treating the mole to mole ratio as a volume to volume ratio, because every gas occupies the same amount of volume. And so instead of writing this whole thing out, you can just say, and this only works for gases, well, 1 decimeter cubed of N2 is the same as 2 decimeters cubed of NH3. So for gases, you can skip a bunch of conversions because the volume to volume ratio is the same as the mole to mole ratio for gases at the same temperature and pressure. And the key thing is at the same temperature pressure. It doesn't have to be STP. It could be some ridiculous temperature, some ridiculous pressure. But if they're the same conditions for both gases, they have the same number of moles. So you can still do the mole to mole ratio like that. So it's just 10. So keep that in mind. So simplify that. Now, is it wrong to do it the first way? No. If you don't see it immediately, I'm not telling you to try to find the shortcut. Do it that way and still get it right. But there are some kind of quicker ways to do that. And like on the multiple choice, when you don't have a calculator, you may want to simplify these things on here. Okay? All the numbers on the multiple choice are designed so you can do them by hand. They end up like being round numbers, like a tenth of a mole or half a mole and things like that, or 2 moles. So like in this kind of problem, you don't need to divide or multiply by 22.7 because it cancels out. Okay. Questions about this? Okay. Let's go into gas laws. Okay. Now, gas laws. Okay. With gas laws, you want to understand the relationship between pressure, volume, and temperature of a system. Okay. The only one of those units where it actually matters what unit is pressure. It has to be in Kelvin. If you're trying to find the relationship between other terms, it doesn't matter what unit they're in as long as they're the same unit. Because pressure and volume units are all factors of each other. The problem with temperature is that it's an addition conversion, not a multiplication conversion. So doubling temperature in Kelvin is not the same as doubling temperature in Celsius. And that's where a lot of kids make that mistake. They're like, oh, 25 degrees Celsius to 50 degrees Celsius is doubling temperature, so pressure must double. No, because you're not really doubling it in Kelvin, which is what we have here. Okay. So pressure versus volume. Okay. At the same temperature, if you decrease the volume, what kind of pressure are you going to get? Increase. Why is that, Mofe? So therefore they do what? They collide more with the container. That's what pressure is. Okay. So if you decrease the volume, more particles collide with the container, which increases the pressure. So low volume would be high pressure. Okay. At very high pressure, what kind of volume are you going to have? The same thing, right? High pressure is low volume. And as you do that, it negatively curves like this because they are inversely proportional. And this is an inverse curve. So P is proportional to the inverse of 1 over volume, meaning that, so let me write some key terms down. It's an inverse relationship. So as P goes up, V goes down. That's the relationship you have here. Now, if you wanted this as a straight line, you would graph P versus 1 over V. And then you would get a linear relationship starting at the origin. So the IB likes to manipulate graphs and change axes to make sure that you understand what you're doing. And so if you graph P versus 1 over V, then you will get a straight line. V versus T. Okay. To keep the same pressure, to keep the same number of collisions with a container, if you increase temperature, what happens to volume? If you increase temperature, what happens to volume? to keep the same pressure, what does the volume have to do? Get bigger. Because you have to give it more space because they're moving faster and you want them to hit the wall the same number of times. You have to make them travel further to get to the wall each time. So as temperature increases, volume increases. Yes. Yes. Um, no. So you can't change all three of them. So like if pressure and volume change, you have to assume the temperature staying constant. Well, if you want them to collide the same amount of times, then you have to make it a bigger space. Because let's say it's colliding like 4 collisions per second, and you increase the temperature, now you're colliding 8 collisions per second. To get back to 4, you have to make it a bigger space for the particles to move to hit the walls. Okay. Now, what's the unit of temperature down here? Kelvin. What does this graph look like if this is temperature in degrees Celsius? What does this graph look like? Okay, Dane? Okay, it's shifted up. So, what were you thinking? Where is the x-intercept? Let me ask you that. Where's the x-intercept? Oh, it's not at the origin. So, relative to the origin, where's the x-intercept? To the right? So, remember, 0 degrees Celsius to the left. So, this ends up being like that because this is 0 Kelvin. And that's how scientists first determined what 0 Kelvin was, because you can't reach 0 Kelvin. What you can do is you can measure a gas at different temperatures and pressures and then just graph the straight line back. And they found out it's approximately 273.15, negative 273.15. You can actually do that experiment as well. Like we've done it in the past, and you can get relatively close to that value. In fact, I was just reading an article, like I just read a Reddit post today that apparently scientists have gotten to 0.0000012 degrees Kelvin with their with substances now, and so they're getting so close to 0 Kelvin that they might be able to study more things about kind of how molecules interact at that. So supposedly nothing moves, but the irony is you can't measure that because any measurement you do puts energy into the system, and so like they're trying to find ways to minimize that and still be able to do it, and so yeah. And to be honest with you, temperature, the way we measure it, is kind of a weird thing because it's the distribution of kinetic energy, like of the particles in the system. And it turns out you can actually have negative Kelvin. Yeah, because as the particles get smaller and smaller, they get less and less kinetic energy theoretically. But scientists have come up with a way to actually energize particles when they're in a very small area. And then when you calculate their temperature, it actually gets you a negative value for Kelvin. But that's okay. So this is a direct relationship because as V goes up, T goes up. And like Mofe was saying, pressure and temperature do the same thing. As temperature goes up, pressure goes up if you keep the same volume. Okay. So again, pressure is proportional to temperature. So it's a direct relationship. Now, here's a trick that I kind of learned in conceptual chemistry, which actually can help you with a lot of different conversions here, not just gas laws, but something I learned in one of my workshops is, yes, P1 V1 over T1 is equal to P2 V2 over T2. That is true. And you could memorize that equation if you want to. But let me show you a little trick that you can calculate without having to memorize this equation. Okay. If you know the relationships, you can do it without knowing that equation. Here's the trick. Let's say we have a temperature of 400 Kelvin, and we have a pressure of 200 kPa and a volume of 10 decimeters cubed. And we want to know our second temperature. And we know our second pressure is 150 kPa, and our volume is 20 decimeters cubed. Okay. Let me show you how you can do this with fractions. Okay, because we're going to have to multiply by all these fractions, like the change in pressure and the change in temperature. Now, what is our pressure doing here? It's decreasing. So our temperature should do what? If our pressure decreases, what should our temperature do? Decrease. So we multiply by the pressure so the number goes down. So how would we set this up so the number gets smaller? How would we multiply by the fraction of these two numbers so that the number would get smaller? 150 over 200. You want to make the number smaller, so that's the way you would do it. What's volume doing here? Increasing, so temperature should increase as well. So you're going to multiply by volume so that your number gets bigger. So what is it? 20 over 10. That's it. And that always works. As long as you understand what's happening relationship-wise, this always works. In fact, this is something I teach my 10th graders a lot about the conversions, because if you know a conversion, you should know whether your number gets bigger or smaller, right? The biggest mistake students make in all math is converting from grams to kilograms. You know, they'll say, oh, 5 kilograms is 0.005 grams. And you're like, that sounds silly, but kids do that. And they just don't think, oh, I just have to convert to 1,000. And they don't think, well, a gram is smaller than a kilogram, so the number should be bigger if it's in grams. Yes, Tamor.
Does it matter which ones are on the top and which ones are on the bottom as long as they're consistent?
No, it does. So it matters which way it's changing. So this is this way, Tamor, because pressure 1 is, so pressure 2 is going down. So then temperature 2 should be going down. So we multiply by this so that the number gets smaller. So we want the fraction to be less than 1.
Oh, okay. You want the
Temperature to go down.
okay. So you have to have a bigger number at the bottom.
Exactly. And then on this one, because volume is going up, then temperature has to go up. So you want the bigger number on top. So yeah, you could memorize this, and that helps you memorize relationships. But if worse comes to worse, you can just kind of do it this way. And this applies to stoichiometry as well. You know, like when you're converting grams to moles, you're multiplying by the bigger number on the bottom because grams to moles is a smaller number. So you're trying to make the number smaller, so you're going to make the larger number on the bottom. And so that's another way that I was taught to do this. So without memorizing P1V1 over T1 equals P2V2 over T2, if you know the relationships, which you should know, you can always make the math work even without knowing that equation. Cool little trick. Not everyone will do it, but helps you reinforce these and then calculate that as well. I'm just looking at that. It's what, 300? I guess it's 600, right? Yeah. I made the numbers really easy because it was like 3/4 and then 2. I'm like, sweet. Okay. Questions about that? Okay. Now, ideal gas law. PV equals nRT. Now, this one, the units do matter. So pressure has to be in kilopascals. Volume has to be in decimeters cubed. N is moles. Oops. R is 8.31 joules per mole Kelvin. And temperature is in Kelvin. What? I think the data packet's always been 8.31. Maybe in physics is different, but let me just double check. Yes, so it's 8.31. Yeah. What? Oh, 0.0821. Uh, that's just a different unit for R. The IB doesn't necessarily like that because the units are all derived in there. Like liters is not a real like an exact unit, and atmosphere is also derived. Kilopascals and like decimeters cubed are like more accurate units. And so 8.31. Now, for this to work for an ideal gas, we assume the following. One, gas particles have zero volume, meaning that in a container, all of it's free space. So if you measure the volume of a container, we're assuming that the gas particles take up so little space that it's essentially that exact volume. We don't have to remove the volume of the gas from the free space. Two, we assume constant random motion, that the particles are constantly moving and they're always just kind of randomly colliding into each other, which is three, elastic collisions, meaning that no energy is lost when the particles collide with each other. That way the temperature stays fairly consistent. If we were to lose heat due to collisions, then our temperature would vary too much. Four, no IMFs, no intermolecular forces of attraction or repulsion. So therefore, everything moves in a fairly linear, predictable way. Well, because okay, in the real world, we have correction factors in the equation. And so I'll show you in a second, like what the actual real world version of this equation is. And so the basis of this is really important because it shows relationships between things, but you're right, no real gas behaves ideally. So the actual like real gas equation is called the van der Waals equation. It has all these other variables to factor in volume, factor attractive forces and stuff like that so you can use it. Okay. And five, temperature in Kelvin is proportional to the average kinetic energy. Okay, and that's something we talked about when we talked about the Maxwell-Boltzmann curve of a sample. So, having said those statements, those assumptions for ideal gas laws, okay, when are real gases the most ideal? At what kind of pressures and what kind of temperatures would gases most likely meet all of these considerations as best as possible? Mofe? Not a specific value, general value, low and high. So low what? So gases are most ideal at what type of pressure and what type of temperature? What kind of pressure would you want? Dave, why low? Right, because low pressure means the particles are very far apart, which means they interact with each other less. So, exactly. You want them to not interact with each other, so you want them as far apart as possible. So, because you don't want intermolecular force of attraction, and you don't want to lose too much energy from all these collisions, so you want them as far apart as possible. Now, what kind of temperature do you want? Yeah, Dan. High temperature. Why? Okay. And when they're moving very quickly, how often do they interact with each other? Not as much because they're moving so quickly in the container. And also, when they're really high energy, if they lose energy when they collide, it's a smaller amount relative to it. So it's negligible. So if you have two high energy particles collide, you lose a little bit of energy. That energy is like can be negligible. So you want particles moving at fast speeds very far apart from each other, so that they don't have these interactions that cause it to behave differently. And that's a big, that's one of the statements the IB wants you to know. Understanding the deviation of real gases from ideal behavior. So the opposite would be true to be least ideal, right? High pressure, low temperature would be the worst scenario for that. Okay. You're welcome. See you. Take care. Good luck today. Okay. They're probably going to get breakfast. So, oh, and they come. Oh, okay, gotcha. Okay, so, let's see. I'm trying to figure out what I want to see. Wait, what? We have to talk about titration, which we'll talk about in a second. But look, titration, I think titration has really bad knack, but it's really just stoichiometry. That's all it is. Like, and so we're going to talk about it at the end to kind of wrap it up. But I'm trying to see obtaining and using experimental values to calculate the molar mass of gas from the ideal equation. Okay, so one more thing here. Okay, PV equals nRT. Okay, now N is equal to moles. Okay, and moles is equal to mass over molar mass. So if we know that's true, we can then rearrange this equation to solve for the molar mass of a gas. Actually, you know what? We're not going to rearrange it. I don't want you to worry about that. What I want you to know is that moles equals mass over molar mass. So if you figure out the moles of gas you occupy, and the problem gives you the mass of the gas, you plug that in to solve for the molar mass. Some some books will tell you, oh, rearrange it so that molecular mass equals dRT over P and stuff like that. Don't worry about that. Just focus on the fact that moles equals mass over molar mass. And so therefore molar mass is equal to mass over moles. So the problem will give you the mass of the gas, and they'll give you conditions so you can find the moles, and then you just divide them to get the molar mass. I'm not going to try to make things complicated here. No need to try to memorize that equation. Okay. The last thing we're going to talk about today is molarity. Okay. Again, molarity is moles of solute over decimeters cubed, 1 decimeter cubed of solution. And so you should be able to convert between all these. Now, key thing, don't write capital M. Bless you. It should be, bless you, moles per decimeter cubed. That is the unit that they want you to write. To avoid any confusion, they want you to write it out in expanded way. So no abbreviations, anything like that. It should be moles times dm negative cubed, and that's the way they write it in the questions as well. No slashes or divisor signs or anything like that. Everything in one line. That way, it's kind of universally understood. Okay. So a titration is just essentially using a standard solution, which means of known concentration, to determine the molarity of an unknown solution through a reaction. And just like acid-base titrations and redox titrations, that's really all it is. You're just trying to find the relationship between what reacts. There's about 6 left, so really don't. Oh yes, Maria. Sorry. Well, I would say it could be 5 or 6 because like what they'll do is they'll break it up into smaller pieces. Like part A will be like calculate the number of moles of the titrant that you used. So you'll give molarity and volume. So how you solve for moles. And then part B will be like how many moles, determine the moles of analyte that were needed to react with it. And then part C would be determine the molar concentration of this. And then maybe part C would be suggest an indicator that would work for this titration. Like that's kind of topic 8, but they would try to incorporate that in there. So it could be 4 or 5 marks. Yes, kind of like that. Yeah. But so with titrations, you can do it any way that you do stoichiometry because again, it's just a reaction. And so like if you have like NaOH plus H2SO4 yields H2O plus Na2SO4, that's just a reaction. All that's different now is you've got like molarities. And so like let's say you have 25 decimeters cubed of H2SO4 and you have 75 decimeters cubed of, that's a lot, but whatever, of NaOH. I should have done centimeters cubed, but that's okay. And let's say this is 2 molar. Okay. You would solve, yeah, it's a lot. So it's okay though. You would solve for the moles of this, and the mole to mole ratio figures out how many moles of this you need. And then you can solve for the molarity that way. Okay, so it's not any different, you know. This is where I kind of taught, like this is where the super equation kind of originated from, because I would say, well, moles of H2SO4, moles of NaOH, it's 2 to 1. Well, M1, M1V1 and M2V2 must equal that. So the molarity of this times the volume of this must equal the molarity of this times that volume. Oh, sorry, I have backwards. The molarity of this and the volume of this must equal the molarity of this and the volume of this in that ratio. That's kind of where the super equation came from. That's where it originated. I'm like, oh, but really, this works for everything because as long as I solve for moles here, it'll work. And so you'd plug this in and you'd say 2 times 75 over x times 25 is equal to 1 over 2. So that's 150 divided by 2, 75. That's not a friendly number. Wait, hold on a second. 150 divided by 2 is 75, and then divide, oh, it's 3. Sorry, for some reason, I multiplied by 25 the first time I cross multiplied instead of dividing. So I was like, how's that working? So this is 3 molar. Oh, yes, Alexia, I did not write my units here. Yes, you're right. The one time that I'm trying to finish up the notes, I decided not to write the units out. I'll remember that, Alexia. Yeah. When you're doing the work, your answer, I would write the correct unit. Like they don't really care what units you use in your work. So if you write capital M in your work, that's okay. But your answer should be the right unit. Like be moles decimeters to -3. So like yeah, I shouldn't have written it like this. I should have written it like that's the correct unit. No symbols or no fractions for units. Always everything with negative exponents if necessary. And if you think conceptually, this number makes sense because here's why. You needed a third of the volume here, but you needed twice as much of this. So really, this does, how do I say this? So this must be 3 times if this were a 1-to-1 relationship because you used a third of the volume. But since it's a 2-to-1 relationship, you need 3 halves as much concentration so these are equal to each other. So it's harder when it's like not a 1-to-1, but if it's a 1-to-1, it's easy to see that. But so like If you have a third of the volume, then you have to have a triple the concentration if it's a 1-to-1. But since it's a 1-to-2, then it's 3/2 of the concentration, which is 3. Questions about that? Okay.